In this video, we're going to solve a ballistics problem. I'll give you the problem and then you can try working on it yourself, and then in the video here I'll show you how to completely solve for this problem. And what the problem is we have a building and we have, say, a cannon mounted on the edge of the building, and we're going to shoot a shell or a cannonball or a bullet or whatever, and it's going to be shot with respect to the horizontal at an angle theta above the horizontal, and it has an initial velocity of v0. That's its muzzle velocity. So the question is how long of time does it take to hit the ground? It's going to go up in the air, reach a peak, and then come back down and hit the ground. So how far away from the building, the edge of the building, is it going to hit? We'll call that x final. The distance from the edge of the building to where it hits the ground is x final. The distance from the edge of the building to where it reaches the peak in the horizontal direction is x peak. And we're going to establish our origin here as x equals 0. And this occurs at time equals 0. The time to reach the peak is time peak, and the time to hit the ground is t final. Now I'm going to establish it when I solve this. The origin for the y is arbitrary. You can make it anything you want, but I'm going to set it equal to the height of the building. That's y equals 0. So any y values higher than that, above that, are positive y values, and any y values below that are negative y values. So the height that the projectile reaches with respect to the height of the building, I'll call it y peak. That is, this distance here is y peak. The height of the building, the top of the building to the ground, is height h. So the values are, we're going to shoot our bullet with an initial velocity of 10 meters per second. It's going to be shot at an angle of theta of 30 degrees. And the height of the building is 50 meters. And the value for g, the acceleration due to gravity, I use the standard value of gravity of 9.80665 meters per second squared. So the question is find all these values. What is y peak? How long does it take to get there? What is the value in the x direction when it reaches the peak? What is the final time that it takes to hit the ground? How far away from the building is it when it hits the ground? And then additionally, what is the final velocity when it hits the ground? It's coming down at an angle, so what's that velocity when it hits the ground? So there's the problem, and see if you can solve it. And you can turn the video off now and try to work on it, or continue on with the video and see how I solve the problem. We're going to now solve a ballistics flight problem. We're going to solve it in a general manner so that will be applicable to other ballistics problems. Now what we have is, say, a building sitting here, and we have a gun or a cannon sitting on the edge of the building, and we're going to shoot a projectile with an initial velocity v0 at an angle theta with respect to the horizontal. Now the height of the building will give as h, small h. That's from the ground up to the top of the building. This is our ground. Now, during flight, the projectile is going to go up, it's going to reach a peak, and then come back down and hit the ground below the height of the building. Now, when solving any sorts of a ballistics problem, we want to set up a coordinate system. So we'll start our coordinate system here at the edge of the building. Now that will be our reference. So this, height-wise, we'll choose to be y equal to 0 at the height of the building. Now, It doesn't have to be there. We could set y equals 0 at the ground or any arbitrary position, but I'm just going to choose it here so that when we solve the equations, that if y is a positive number, it means we're above the height of the building, and if y is a negative number, we're below the height of the building. But if we chose our reference to be the ground, then all the y values would always be positive. But again, that's arbitrary. Now, our x equals 0 position will be here. So the projectile is at x equals 0, at t equals 0. It's going to reach a peak, and the peak will be at position xp at time t peak, and then it'll reach the peak and then start coming back down, and it'll hit the ground here at t final at time t final. Now, few points to keep in mind. The key to solving any sort of a free flight or a ballistics problem is to understand that you break your motion up into components, into an x component and a y component. Now there's only one force acting on the projectile. We're going to neglect air resistance and other forces that might influence the trajectory of the projectile, like a bullet or a cannon shell or throwing a ball at some v0 at angle theta. We're going to neglect air resistance, so the only force acting on a projectile once it's thrown up into the air or released up into the air is a force of gravity, which tends to pull the object down with an acceleration g in metric units. G is 9.80665 meters per second squared, or around 32 feet per second squared in English imperial units. Now, there are no horizontal components to forces acting on the projectile, and that's a key point. The only force acting on a projectile is that in the vertical direction. The horizontal or the x direction is unaffected by any forces, which means then that the x component of velocity remains constant forever. If there wasn't any gravity pulling the projectile down, that projectile would continue on forever with the x component, the initial x component of velocity. That's a key point to keep in mind. Now, that horizontal component of velocity never ever changes. So we're going to break up our velocity into two components. Here's v0 at angle theta. Our y component, we'll call it v0y, is v0 times the sine of theta. And the x component of velocity is v0x, which is v0 times the cosine of theta. This component never changes. The x component remains constant at v0 cosine theta forever, but the y component of velocity will change with time, because we have the initial y velocity shooting upward, and because of the acceleration due to gravity, it slows the projectile down until it reaches a peak. The y component velocity at this point is 0, and there's only a horizontal component of velocity at that point, which will be v0x. That's the only velocity of the projectile at this point. It peaks out, there's no more vertical component, and then it will start falling down and gaining more and more vertical velocity as it accelerates downward due to g. So, we have then the problem all set up here. Now we're going to break it up into two intervals. There's the interval from x equals 0 to x equals the peak, where it reaches the peak, and then from the peak to when it crashes and hits the earth at the final time. Now, we use Newton's laws of motion to show us how to solve this problem. The first law tells us that an object in motion remains in motion or at rest remains at rest unless acted upon by an outside force. That is why we can say that the x component of velocity never changes, because there's no force acting in the horizontal direction to change the horizontal component of velocity. So what we have then is that g is an acceleration. Okay, the distance, let's call it x. The second derivative of x with respect to time is, or not x but y, we're in the y component. The second derivative of y with respect to time is equal to minus g. Downward is the minus direction, upward is a positive direction. So our acceleration due to gravity is in the negative direction. So if we integrate this once, we have dy dt is equal to minus gt. This, the rate of change of position with time, is velocity. So this is v in the y direction. It's minus gt. And if we integrate this plus some constant, which we'll call an initial velocity in the y direction. And then if we integrate this a second time, we get y as a function of time, and this is minus g t squared over 2 plus the initial velocity of y times time plus some initial y. These are our key equations here. We have the velocity equation, we have a position equation, and we have our acceleration equation. And we'll be using these to solve this problem. So, we're going to now look at time from t equals 0 to t equals t peak. And we're going from x equals 0 to x equals x peak. In this case, we're looking in this interval here. So, our velocity in the x direction is v0x. That is the component acting in the x direction, and this is v0 times the cosine of theta. The initial velocity times the cosine of theta. The velocity in the y direction is minus gt plus some initial position in the y. Or not position, but initial velocity in the y direction. So this is plus v0 in the y direction. Now, our position equation, y as a function of t, then becomes the initial velocity in the y direction times time minus gt squared all over 2 from this equation, plus some initial y position. Well, in this case, since y is equal to 0 at the position of where we're shooting, the y0 position is just equal to 0. Y is 0, so we don't need that part there. That's why I chose the origin for the y to be in line with the top of the building. Now, our x of t position is, since the velocity in the x direction never changes, this is the initial x velocity. This would be v0x times time. And our v0x is the initial velocity times the cosine of theta times time. And then in this equation, our y0 is v0 sine theta minus gt squared over 2. And this equation becomes the initial velocity times sine theta minus gt. So those are our equations that we'll be using. Now, at the peak of the flight path, when the projectile has reached this position, the y velocity is 0. So that allows us now to solve for the time that it takes to get there. Our y velocity is given by this equation. Well, at the peak, at Vy, at time to the peak, is 0. And so that is v0 times the sine of theta minus gt. So we can solve for t on this equation. v0 is known. The angle of that the projectile is shot up is known, and g is known. So then t is equal to v0 sine theta divided by g. That gives us the time to the peak. So here's our first known quantity, the time that it takes to get to the peak. That's to this point. That's how long it takes for the projectile to move this far. Now, what about how high does it reach? Well, once we know the time that it takes to get to the peak, we can now put in this equation to solve for y. Now we have the time that it's taken the projectile to reach the peak of its flight. And at the peak of its flight, it reaches a height of y peak, or yp, and it is advanced a direction, or along the x direction, a distance x peak. Now that we have the time that it's taken the projectile to reach the peak of its flight, we can find out how high it has flown upward by using this equation here for our vertical flight distance. So y of t is v0y times t minus gt squared over 2, or v0 sine theta. This is our initial y velocity times time minus gt squared over 2. And now we put in the peak time, or the time to reach the peak, into that equation to get how high up the projectile has advanced. So then, our y at t peak, we'll call it y peak, that is equal to v0 times the sine of theta, and we put in for t peak, which is v0 sine theta. So v0 sine theta times v0 sine theta is v0 squared sine squared theta all over g, minus g over 2 times t squared, which is v0 squared sine squared theta all over g squared. Now we can see that these two terms are the same. The g here cancels with one of the g's there, so we have v0 squared sine squared over g minus v0 sine squared over g 1/2. So this just becomes y peak is v0 squared sine squared theta all over g. So we now have or over 2g. We're subtracting 1/2 from this, so it's v0 squared sine squared over 2g. So that is our height, the maximum height. So we now have another piece of information right here. Now, how far does it go when it reaches the peak? So what is our x peak? Well, the x peak will be when we put t peak into this equation. So in this case now, x peak is going to be v0 times the cosine of theta times the time to reach the peak, which is v0 sine theta. So we get a v0 squared and then a sine theta all over g. So that's the time or the distance it travels once it reaches the peak. Now we could write this using a trig identity. We know that the cosine of 2 theta is sine theta cosine theta. So I could write this as v0 squared times the sine of 2 theta all over 2. That's another way that we could express that. Over 2g. So we have all the information we need now. Let's summarize this to get this part of the flight. Now I'm going to put that over here. So we have that t peak, the time to get to the peak, is v0 sine theta over g. That the height that's reached is v0 squared sine squared theta over 2g. And the distance in the x direction traveled when it reaches the peak is v0 squared times the sine of 2 theta all over 2g. So this is for this part of the flight here. Okay, now I have summarized, we have our summary here of the equations that we derived during this interval of travel, where we go from time equals 0 to time peak. So these equations are valid between the interval 0 and the time that it takes to reach the peak. Now, what we need to do is write our equations for the interval of time starting at the peak and then progressing in time until it hits the ground. Now, we can recognize, I'll put this also in another form, that these, remember, v0 sine theta is the initial velocity in the y direction. This is initial velocity in the y direction squared, divided by 2g. And this is v0 in the x direction times time to reach the peak. So, two forms of the same thing. Now, we're going to look at the flight after it's reached the peak. Now, we're starting from t peak. We're starting our time counter at this point. So, we're going to be going between the interval where it's reached the peak to when it hits the ground at its final time, and then x goes between x peak and the final time, between x peak and the final position when it hits the ground. So we'll start now with what we know. We know that the time to reach the peak was v0y over g, and we know that the peak value is g over 2 times t peak squared, and if we put this in there, this is g over 2 v0y squared over g squared, and one of the g's cancels with the g in the denominator, so we can write this as v0y squared over 2g. Now, how about the equation for vertical height as a function of time? Well, v or y as a function of time then will be, we start at our initial height, which is y peak. This is y peak. So we're at y peak, and we're decreasing by the amount of acceleration, g over 2 times the time squared. Well, the time is the time that we have minus the time at the peak, because we're starting our counter now at the peak. So this now becomes t minus t peak squared. How about x as a function of time? Well, x as a function of time is still v0x times time, and again we're starting our counter from here. So we put in for v0x, which is v0 times the cosine of theta times time. Now the velocity in the y direction will be the initial velocity, v at time peak, minus the acceleration times time. But what is this? This is 0. Remember, we're at the peak. So the velocity in the vertical direction is 0 when we're starting out from the peak. So that is 0. So we have minus g t minus t peak for the vertical velocity. And our velocity in the x direction is still v0x as it was before. That never changes. Now, when the projectile hits the ground, what happens? Well, we know the final vertical position in that case. Y at the final time is going to be minus h. Remember, here's our reference. This is y equals 0. The distance from here to here, the height of the building to the base, is h. So if this is y equals 0, this is in the negative y direction. So the final position in the y direction is minus h. And that happens at time equals t final. So we can put that in to our equation here for the vertical height. So we have minus h is equal to the y peak value minus g over 2. At this time, the time is t final minus t peak squared. Well, we know t peak, we know the y peak value, and we know h. Those will be given. So we can solve for t final. Well, this is quadratic, and what we could do is, let's just go ahead and put this together. So we can move this to the left side and this to the right side. So we have y peak plus h is going to equal g over 2 t final minus t peak squared. So our final, if we want to solve for this t final, we take and we move. Let's see what I can do. I'm kind of running out of space here. We can get rid of this part here. So what we're going to do is solve for t final. Well, we're going to move the 2 and the g over to the left side. So this is 2 over g times y peak plus h, and that's equal to t final minus t peak squared. Well, if we take the square root of both sides, we get rid of the square root here, and when you take the square root of both sides, you end up with a plus and minus root. So the final time then will be t peak minus plus or minus 2g y peak plus h. Now we can decide which sign to take, plus or minus. Well, the final time has got to be greater than the t peak time. Time is progressing, so we choose the positive sign here to give us the right value of time. So we have our final time in terms of the time to get to the peak and the height at the peak. Now we can also write this in another form by noting here that there's a relationship between the time to the peak and the peak y velocity. Is if we take t peak squared, we get a y squared over g squared. So this could be written as t peak squared. If t peak is squared, we got y0 or v0 y squared over g squared. So this would be g over 2. So we could put that in for y peak here if we wanted to, and we multiply through by 2 over g. So this could be written as t peak plus the square root of t peak squared plus 2h over g. That's another form that we can write that as, because we have 2g times y peak, 2g times y peak cancels that, so we get just t peak squared. So two different forms for the final time. Now, how about the time now, or the distance? Let's find xf. Well, that's given by this. So we take our final time, this expression, and multiply it by v0 times the cosine of t, or v0 times cosine, or just vox. Vox times t final. So we can write this as so we've used that equation. So we can use this so that x final then will be v0x times t final, or vox. Well, I'll just write it as that way, because all we have to do is substitute that in for t final. So that's our vox, or our final distance. We just take our initial velocity in the x direction and multiply by the time that it takes to hit the ground. How about now for the velocity, the final velocity when it hits the ground? Well, that's going to consist of two components. Velocity in the x direction, velocity in the y direction. So the velocity in the y direction will be when t is equal to t final in this equation. So we will call this Vy final is going to be minus g t final minus t peak. Well, we have an expression for t final minus t peak right here. T final minus t peak is just this radical. So we can write this as minus g times the square root of t peak squared plus 2h over g. Or we could put that radical. But doing this, if we move g into the radical, it becomes g squared. So this is minus the square root of g t peak quantity squared plus 2hg. We have a g squared that distributes throughout in there. Now, what is g times t peak? Well, g times t peak is just the initial velocity in the y direction. So we could also write this as v0 in the y direction squared plus 2gh. Another form for the final velocity in the y direction. Well, the total velocity, this is our final velocity. Well, the final velocity squared will be the final velocity in the y direction squared plus the final velocity in the x direction squared. So the final velocity squared is going to be final velocity in the y direction squared, which is this. We square this, so we end up with v0y squared plus 2gh, and the final velocity in the x direction is vox, and that's squared. Now notice, voy squared plus vox squared, what's that? That's just our initial velocity. Remember that v0 squared is vox squared plus voy squared. So this just becomes our initial velocity squared plus 2gh. So the final velocity then is the square root of the initial velocity squared plus 2gh. That's another final form that we can have here. Now we're in a position where we can collect all our equations and put it all together. And I'll do that here. I'll get these equations written out on the board here. So here's the summary for the equations of motion of ballistic flight that we just derived. Now, in this interval of time between time equals 0 and time to the peak, when the projectile is initially shot up and rises to the peak, these equations hold between 0 and t peak. The peak value that the projectile reaches with respect to our datum, y equals 0, that's this distance, that's the y peak, it's given by this equation. Also at the peak, we notice that the y velocity, the y component of velocity is 0. The x component, in this case, will be just v0x, because remember, it always travels at the same velocity in the x direction. The distance it travels horizontally to get to the peak is this. We just take the horizontal component of velocity times time peak, which is this. And we could also write this in this form, is this would be vox times t peak, which is voy over g. Which is kind of an interesting form, is just by multiplying vox times time peak. It's just the initial component in the x direction, initial component in the y direction divided by g. That's how far it travels to get to the peak in the horizontal direction. Now, in the interval of time between the peak and when it crashes to the ground, hits the ground, that's this interval. So this is for time between t peak and t final. These equations. Here's the time that it takes to hit the ground at this point. It's the time to get to the peak plus this amount. We have two forms there. The total distance traveled horizontally is given by this. VOX, initial velocity in the x direction, times time, final time. So we put in this for final time and multiply through by VOX. VOX times t peak is x peak, and then VOX times this component. The final component of velocity in the x direction is just the initial component of the velocity in the x direction, as it always remains constant. And the final velocity in the y direction, we calculated out to be this, and here's two different forms for that. Now the final velocity is the square root of the sum of the squares of these two, and we just showed it to be that it's the square root of the total initial velocity v0 squared plus 2gh, which is an interesting form. So now we have everything we need to solve the problem that was given. Now, remember, the initial problem is that the initial velocity is 10 meters per second. The angle, theta, is 30 degrees. So theta equals 30 degrees. The height of the building is 50 meters. And then we know that g, in all these equations, g is 9.80665 meters per second squared. So g equals 9.80665 meters per second squared. So all we have to do is plug these values into our equations. If we do that, t peak is just v0 sine theta over g, or 10 times the sine of 30. Sine of 30 is 1/2. 1/2 times 10 is 5 divided by g. So 5 divided by g, this gives us 0.5099 seconds. All right, how about the VOX, the initial velocity in the x direction? Well, that's v0 times the cosine of theta, or in this case, cosine of 30 is square root of 3 over 2 times 10. Square root of 3 over 2 is about 0.866. So this becomes, we could write it as 10 times the square root of 3 over 2 meters per second. How about, how far does it travel in the x direction when it gets to the peak? Well, x peak is just v0 in the x times v0 in the y divided by g, or just v0x times peak. So we could take this number times this number, and so this becomes v0x times the peak. There's our v0x, here's our time to the peak. We multiply those together and we get 4.4155 meters. So this distance is 4.4 meters roughly. How about the height? What's the height above the roof that it reaches? Well, y peak is the initial or the time to peak squared times g over 2. Putting those values in, we get 1.275 meters. How about the final time? The final time is we put in these values here. We've got t peak, then we have t peak squared, 2h over g. Well, h we know is 50, and we know g, so we can put those values in. So the time, the final time, the time that it takes to travel and hit the ground is 3.744 seconds. I'm just rounding the numbers. How about how far does it travel in the x direction? Well, how far it travels in the x direction is given by this. And if I put in the numbers, this comes out to 32.42 meters. And how about the final velocity? That value. Well, final velocity is v square root of v0 squared plus 2gh, and that works out to 32.87 meters per second. So that's our ballistics problem. There's all the values from the derivation, and also note that in any ballistic flight, any free flight, the path of the trajectory is always parabolic, and it's symmetric about the peak. That is, if I were to go from here to here, the time that it takes to get from here to here, which is t peak, is also the time that it takes to come back down to the same spot at the same level, because of conservation of energy. So the time interval here is t peak. The time interval to get to this point is t peak. And then there's a little extra time because it's to hit the ground, because it's yet traveling further in the y direction. So there you have it. Now we'll do another trajectory problem that's a little more complicated, where we have a building over here and we want to hit something on top of the building. So we use the same equations, but I'll go through it again, solving that problem in the next video.